Today, we're going to talk about spherical coordinates. That's the last topic for the exam on Monday of next week. Remember that they're like, you can find the practice exams on my lab, and the solutions for those are already posted on the department website. And also on the department website, there are like two more practice exams PDF, so you can also see those as well. Spherical is 15.7. So before it just if you look at the, like, it's kind of like the structure of the exams are always it's more or less like, if you look at the practice exams, it's more or less like predictable, in the sense like there probably will be like a Lagrange multiplier problem, and then like two double integrals, two triple integrals, and things like that. Then oh, the NU means non-upload. So those are like problems that you wouldn't upload your solutions to. And the upload one, because remember the exam has two parts. So the first part is non-upload, and the second part is like upload problems. So it just to sort of say like, oh, this would be like non-upload problems, and the other would be like upload. Which sort of like it was just trying to be broken into a, like the practice exams were broken into a way that like would look similar to how you would find them on the actual exam next Monday. Is that making sense? No. Like first, no. That's why if you check out the announcement, that's the idea. First, there will be like an you'll see on my lab an exam called non-upload. After you finish that one, then the upload exam will appear. So it is broken like into 2, 3, yeah. So yeah. Sort of a structure. It is 2 questions. I think you have 25 minutes. But that one is you don't have to submit your. I mean, that one you don't have to upload anything, and it is designed so that it requires less calculations, just to put it like somewhat, to put it mildly. And then like yes, that although that's not take I think that will happen, although respondents is obviously like, you know, that doesn't interfere with the actual exam time. But yeah, I think for each part you have to do respondents again. And then and the upload is 3 questions. It's let's see. I don't know if you have seen the announcement. Here you go. Here are the solutions to the five practice exams on my lab. Here are 2 more practice exams, and you are taking the online exam. So here's the information. And then here are the sections for the exam. Is that okay? What else? Yeah. Oh, and here's a study guide for the exam as well. So, but you just have to go on the department website, just start reading like the stuff that says November 14, 15 exam. And remember, you still can use your like 2-sided piece of paper where you write formulas or whatever. So Let's see. Okay, so let me start like just with a little bit about spherical coordinates, showing you how they look like. Okay, so let's see, where's the point? Yeah, no. This is so weird. The orange point you're plotting, I don't see it. Ah. Oh, okay, here it was. Yeah. So here's this like spherical coordinates, like, well, the name should probably tell you all of it. It is like a version of coordinates that interacts nicely with spheres, right? So there's one of the like one coordinate is sort of like a radial coordinate, and the other is this one that you see called rho on the animation, and the other two coordinates are like more like angle like coordinates, and those are like versions of latitude and longitude on the surface of the earth. So rho, it is the distance of a point to the origin. So for example, rho equals 3, right, means like all the points, if you just like said, oh, this point has rho equals 3, that means that this point has a distance of 3 to the origin, right? And so as you change the value of rho, right, you're changing the distance a point would have to the origin. Okay, so let me show you a point, a particular point. Let's like right now, this point per se does not matter too much. The only thing that matters is like that its distance at this moment is 1.9. So that's the value of rho. So you see, if I increase rho, what I'm changing is like the distance of this point would have with respect to the origin. Is that making sense? So rho is like an actual like radius. Okay. Then there's an angle theta, which is like the angle theta that you know from polar coordinates. So it's this angle that's being measured here, like on the XY plane. If you see here theta, okay. So by changing theta, like, okay, so let's say here's theta equals 0. So that's aligned, the point is aligned with the x-axis, right? And if you start changing theta, you just start moving the point, right? Like now at pi over 2, it's like here on the y-axis, and if you keep moving it, like you get to the other axis and things like that. Okay, so theta is like the same theta as in polar coordinates. So that one is not too bad to remember. And then there's the one that's truly new one is this angle phi or phi, which you see here. And that's sort of an angle that starts like sort of at the North Pole. Okay, so imagine like an angle. So it's a summation of many circle. Oh, well, you can like it depends on what you're saying. It's the summation of circles. Like you can think of like as you move rho, you get like a bunch of spheres, right? But those would not be circles, right? They would just be like sphere cross sections, if you want to think about it like that way. But you don't, I mean, the sphere is just their shells. Yeah, yeah. The sphere is just there to sort of illustrative purposes. You don't need to see the sphere like to find the point. What I'm saying is that there's this angle phi or phi, which its value is 0 when it's aligned with the North Pole. So here, imagine that when the point is at the North Pole, the value of phi equals 0. And then you see like it keeps changing values. As you move towards the South Pole, as you move along a meridian, if you, I don't know how much you remember from cartography, but this is like this line that I'm drawing here. Yeah, it's like an angular coordinate. I don't know if it's the same sense in which they use it in statics, but I wouldn't be surprised if it's like the same. But like the point is that as you're moving towards the South Pole, the phi increases. Okay, so by the time you hit the XY plane, right, you have dropped by 90 degrees, right? So you have dropped like by pi over 2. And as you move towards this, South Pole, you have covered pi radians. Okay, so the phi from this angle phi goes like essentially goes from 0 to pi, because that's what you need to go from the North Pole to the South Pole. Is that making sense? And you say, why is it not to like because with theta you can sort of move this point around, so you can use theta to cover all of space, and you just get phi to move it like vertically more. That's kind of like the point. Is that making sense? So you only need phi to go like theta will still go like from 0 to 2 pi as usual, but phi only needs to go from 0 to pi, and that way you get anywhere that you want. Is that okay? This bottom slider, you mean? Like the one that says slide to pull plot? That's just to show you how the point is created. It doesn't have like, it's drawing for you like the point in real time. So it's saying,
the steps of future calculations that we're gonna do. Like first, there's yeah, I don't even which distance is being calculated for second and third.
I mean, that's why I didn't like this slider. Like that's why I didn't like I was not doing it in real time, because like that's just how the app is doing it, right? Like the idea is like if you have a point, right, rho gives you the distance to the origin, right, and then theta just gives you like it's the same angle that you see here on the XY plane from polar or cylindrical coordinates, right? And then phi is like this angle between the z-axis and rho. I'm about to draw it on the iPad, but you don't like yeah, like this this slider is sort of is creating it in a odd fashion, so that's why I didn't focus too much on how it was like the point shows up on the animation.
Thank you.
Sure. Yeah, I don't think they're like oh, and then like just so that you see like there's I did a YouTube video about this, but like definitely this is not worth like doing in class. You can sort of find like the pieces of volume of in spherical coordinates. The pieces of volume will look like this, these yellows, these red pieces. Okay, and I'll give you like the formula for what that is in a second. But can I change this somehow? But so you see, like they're like they're cute, but like yeah, there's like a formula for them that one can find, which is fun to find. But that's sort of like what will go into DV. But what for that you need like the formula for the surface area of a sphere and other things. So it's a cute exercise, but I'll just read what the formula is. But like this is how, you know, in Cartesian coordinates, you sort of break the space into mini boxes. Like in spherical coordinates, you're breaking the space into things like that look like this. Okay, so let's go back to the iPad. So basically, here's the idea of spherical coordinates. If you see a point X, Y, Z, there's one of the variables is called rho. So this is the distance from the point to the origin. Okay, and that's just like the, I don't know if you remember like Pythagoras theorem. I think we did it in, I mean, we did it before with vectors. So this is just a square root of x squared plus y squared plus z squared. Okay, that was like the formula for the distance of from a point to the origin, right? Or like if you think of this is like also the norm of the position vector. If you want to think of, I don't know if you remember this from the beginning of the course, but if you think of this like vector as r, that was the norm of it. So that's like the name for, that's what rho means. Okay, and then when you look at the shadow that this point makes on the xy plane, so there's a shadow here, x comma y comma 0. Okay, and so there's some angle theta. So theta is the angle from polar coordinates. And there's a new angle. So this theta is between 0 and 2 pi. And then there's a new angle, which is phi. Which is the angle between, well, it depends on what you're saying. It's just a series of projections. I mean, you can think of theta as being determined as the angle between, you know, the x-axis and this shadow that the vector makes on the xy plane. And then phi is just like the angle between the z-axis or the vector k and the position vector. Okay. So so this phi is an angle between 0 and pi. And when phi equals 0, you are at the North Pole. When phi equals pi over 2, you are at the equator or on the XY plane. So the XY plane. And when phi equals pi, you are at the South Pole. So like the only thing that can be a bit confusing about phi is that it starts at the North Pole. That's the only thing you have to remember. Like that can be a little bit weird. Is that okay? Yes, this is all in radians. Yes. Or 0 radians. Yeah, yeah. Positive z-axis is 0 radians. Yes. So I don't know if yeah, sorry, this like in this case you can include pi, correct? Yeah, yeah, good point. Good, thanks. Oh, good, perfect. So now I don't know if anyone notices like what this blue segment is like in terms of variables that we have used before. What's the length of this segment, this blue segment? It's r, right? Like this blue segment is r from cylindrical coordinates. So secretly there's like a triangle that you can draw. Yeah, this is how we're going to find them. Good, good, good. Excellent. Well, it's with let's like there's a right triangle here secretly that I'm going to color in yellow. So let's draw it separately on this side where you have z, you have the angle, the variable rho, and then you have r, and so here you have phi, and then you have a 90-degree angle here. So what does that tell you? That what does this tell you? That what is cosine of phi? Cosine of phi equals z over rho, and that and what is sine of phi? Sine of phi equals r over rho. Okay, so in fact this gives you already like some relations which are going to be used in a second. So let me write them here. So if cosine, yeah.
In the middle of this, what are we trying to find? Just the area of the yellow triangle?
Oh no, not the area. It's just like I'm trying to use basic trig to relate the variables. I was just trying to show you like what triangle I'm referring to, so that's why I color it. I'm just saying I can use this triangle to find like a relation between z, rho, and phi. right? Like what I'm trying to say is that, like, for example, if you look at the first equation, right? The first equation is saying that z equals rho cosine of phi. Is that making sense?
Yeah. So we're
that-
just changing X, Y, and Z into
Right.
these new variables.
Yeah, I'm just showing you how you would how would you rewrite x, y, and z in terms of rho, theta, and phi. So like this is giving you z as a function of well, the Greeks made many contributions to mathematics, although they so it remains like that. The good thing is like because of the fraternities, you sort of remember the names of the letters, I suppose. But yeah, I'm just showing you how to rewrite x, y, and z in terms of the new variables, right? And then if you look at the second equation, if you look at this equation, it tells you that r, the r from cylindrical coordinates is rho sine of phi. Okay. And so how is this useful? Because remember, and this is like the dictionary. So sorry, this is now we're ready to write the dictionary. So remember that x was like r cosine of theta in polar or cylindrical, but r becomes rho sine of phi, right? Let's put it like this. Like what I'm trying to do here is Cartesian, cylindrical, and then here's spherical. So x as x is in Cartesian, in cylindrical you write this as r cosine of theta, and in spherical r becomes rho sine of phi, and cosine of theta just keeps being cosine of theta. So you just write it like this. Let me use a different color here, maybe. Okay, so what I'm saying is that in spherical coordinates, if you want to write x in spherical coordinates, you write it as rho sine of phi cosine of theta. Is that making sense? Then r again becomes rho sine of phi, and sine of theta is just sine of theta. Okay, so this is again good because in spherical coordinates, like again, the variables are rho, phi, and theta. So you're rewriting y in terms of rho, phi, and theta. And in cylinder, if you the last one, right, z in cylindrical is still just z. Remember that have made no change. And so in spherical it becomes rho cosine of phi. So this is like the key table, or like the thing that you really need to know or memorize or just write down somewhere. Okay. This is like the dictionary between like all the different coordinates we have been using thus far. And in fact, if you want to continue this, remember the dv in Cartesian was like dz dy dx, right? In cylindrical, I don't know if you remember, it was r dz dr d theta. If you want to add like another row to this thing. And again, in spherical, it's actually a little bit more tricky to understand why the formula is this one. There's a YouTube video I did about it, but you can also find a bunch of YouTube videos about this. But in spherical coordinates, like the formula for the volume is rho squared sine of phi d rho d phi d theta. So let me write this carefully because it's the first time you're seeing it. Okay. So that's like how dV gets written in the different like systems, right? Well, again, not without going into too many details. The reason why rho is squared is that again, this is not like the full explanation, but at least it's some explanation. If you look at the units, right? dV has units of volume, right? Rho, because it's distance, it's like length, so this has units of length. Right, dV is like for volume and dA is like area. So like dV is like what appears in triple integrals and dA is what appears in double integrals. So what I was saying is that d rho is has units of length. Well, this will be related to the Jacobian. It's like a special case of Jacobians, yeah. But that won't be on the exam. We'll start the Jacobian next time on Thursday. So this has units of length. This is an angle, has no units. This is an angle, has no units. So up to this point, all of this has length units. And then you need to get to volume, the only variable that you can multiply by that has units of, like you need like, the only variable with units in spherical is rho. So that's why you need like a rho square to get units of volume. Is that making sense? So that's why like there's a rho squared in this formula. Okay, so let's do like just a warm-up exercise so that you see how this works. And maybe just to like, again, if you want to add another row to this table, just remember that rho squared equals x squared plus y squared plus z squared. That's a useful one to keep in mind. And that r squared equals x squared plus y squared. Those two are like useful formulas relating like the rho and r to x and y and z. Okay, so let's find the volume of a sphere radius r. So let's do an example. So I don't know if anyone remembers the equation. Oh yeah, you can also say, right, that's another one, a good, it's true and also useful. You can also say that rho squared equals r squared plus c squared. This is correct, yes. Good, let's add it to the list. Yeah, that one is, it can be useful sometimes if you're switching from cylindrical to spherical, yeah. Good. So what's the equation of a sphere radius r? Is x squared plus y squared plus c squared equals r squared. Okay. So here, like when we do an like what is like we're going to integrate the volume, right? So like the volume is going to be the integral of dv. But as I just told you, the dv in spherical is rho squared So this is the formula for the volume in spherical coordinates. So again, what you have to do here is very similar to what we have done in the past. So what we're going to do now is going to integrate this first with respect to rho. And so, you know, the types of arrows that you have to draw now are like radial arrows. So like it's like a 3D version of polar. Like imagine you place like a candle or like a light bulb at the origin, and you draw and you start drawing like a bunch of light rays.
Professor,
Yes.
why is it p squared sine theta?
Well,
I mean, rho squared sine theta.
well, as I was saying, like at least the rho square factor is needed so that you get the volume here. You see, because you need something that has units of volume, right? The rho has units of length, but the angles have no units, right? So this only gets you this part. This part only has units of length, right? So you need to multiply by something that has units of area to get volume. So that's where the rho squared comes in. And the sign of phi is a little bit more complicated to explain. It's like, it's just because of it, like there's sort of like a distortion when you find like the volumes. But like what I'm trying to say is that there's like a rho square here. So the rho square, the rho, that those two things combined gives you volume units. Is that making sense? Yeah, this factor is not, I'm not explaining where this factor comes from, but it sort of shows up when you start doing like the calculation carefully for what the volume is. But at least the rho square is there so that the units come right, basically. What I was saying is that like the way in spherical, how you're going to find the bounds is that you're going to draw like light rays emanating at the origin. So to find these bounds, so like if you look at the like in the case of the sphere is kind of easy, because in the case of a sphere, you know, well, where are all the light rays starting? They start at rho equals 0, right? They start at the origin. The origin is part of the sphere. So the first bound for the sphere in spherical coordinates is, I mean, for this volume is rho equals 0. But and then where do the light rays exit this region? They exit through the equation of the sphere, right? But what's the equation of a sphere in spherical coordinates? What does this become in spherical coordinates? Rho squared, good, because that's exactly what the table sheets gave you upstairs. So you get rho squared equals r squared, so rho equals r. right? So this is like the version of a circle, right? Like the equation of a circle in polar is like r equals 4 or r equals 1. In spherical, the equation of a sphere is like rho equals 3 or rho equals 5. So you get rho equals r. You see? Is that making sense? So the bounds for rho are like from 0 to big R, where R is like the radius of this sphere.
How come it's not rho equals to the x squared plus y squared plus z squared, but in polar coordinates
Well,
or spherical coordinate format? So like, why isn't it rho equals to the square root of rho sine phi cosine phi squared plus?
oh, right. Like, oh, yeah. You can make you mean like you can you can replace rho squared, like you can replace x with rho squared sine square of phi cosine
Yep.
square of theta, right?
Yep.
Oh yeah. If you want you want to see that,
But that would be like the full equation for rho equals r, right?
yes. Like what happens is this. This is what you wanted to do, right?
Yeah. Yep.
One does this once in your lifetime and then never do it again. But like this is basically what you get if you just plug in everything, right?
Yep.
You factorize the rho squared because there's a rho square everywhere, right?
Yep.
And then what else can you factorize? You see, you can factorize sine square of phi in the first two, right?
Okay.
So you put sine square of phi in the first two, and then you get cosine square of theta plus sine square of theta. So what happens with this? What happens with this parenthesis?
Never mind.
It becomes 1, right?
Well, and then you get another one because you
Yeah.
got the sine squared plus cosine squared
Yes.
phi.
Is that making sense?
Oh God.
So that's why
Okay.
that's why x squared plus y squared plus z squared equals rho squared. If you
Got
want. Yeah. Is that okay with everyone? So this is an aside. Or you could trust me and just use that rho squared equals x squared plus y squared plus z squared. But yeah, it's the same. Yeah. Is that okay so far so good with everyone? So those are the bounds for rho, and then the bounds for phi are just what you have to right there is like well the values that like the angles that you have to move these rays around to to sweep out the entire like ball or like the entire interior of the sphere, right? So you see, like you have to draw arrows at angle 0. You have to draw arrows, like you have to draw arrows in all directions, right? Because it's a sphere. So essentially, like you need like to go from 0 to pi for phi, because the arrows are being drawn like along the z-axis, along the equator, along the negative z-axis, like it goes everywhere, right? So that's why the bounds for phi are from 0 to pi. No, the next example will be one where it's not from 0 to pi actually. And then what are the values for theta? Well, again, like the sphere or like the ball is in the everywhere, right? In all the quadrants. So theta also has to go from 0 to 2 pi because now it touches like all the quadrants, right? Is that making sense?
And that's because we have a perfect sphere centered at the origin. Say if it was like a sphere, would
Right.
have. Okay.
Yeah. Yeah, we can do I can do a variation in a second to show you how the bounds change. And now this is like an easy integral to do because first you're integrating with respect to rho. So what's the integral of rho squared? It's rho cubed over 3, right? And 0 to pi for phi is because it's not just the 0 to pi is because the sphere includes both you have to move the angle from the North Pole to the South Pole, and that takes pi degrees. And then what's the integral of sine? That's negative cosine, right? So you get r cubed over 3, the integral from 0 to 2 pi of negative cosine of phi. And so what do you get that when you evaluate it? You get 2. So you get 2r cubed over 3, 0 to 2 pi of d theta. And so you get 4 pi r cubed over 3, which some may recognize as the formula for the volume of a sphere, right? Is that okay? Good. Do a different one that will like satisfy many uncertainties people have about the bounds. So let's do the following. Let's say this is another example. I give you the cone, and I also give you a sphere, let's say of radius 1. Well, you'll see this one. And so let's find an integral that gives you, the volume of the region inside the sphere, but below the cone. Below the cone. Okay. Oh yeah, you should always draw. So let's try to draw them. So what if let's start with the cone, right? Well, let me start first by drawing XYZ. This is the cone, right? Let's see. Is this going to work? Maybe I need to make the sphere a little bit bigger. Let's try this one out. Oh yeah. Okay, sorry. I'll do it this way. Well, will that help? Yeah, what I want is okay. Let's leave this cone and then we'll do a different one. Okay, I'll keep the sphere nice and easy for now. Then I'll use a slightly different sphere. Okay. Yeah. The thing is, like, okay, let's just play it, like, take things one step at a time. So just to make this more friendly. So this is a sphere of radius 1, center at the origin again, right? So essentially, it's like if you had like the think of the think of the sphere as like an orange or an apple, and then you are like putting like a cone on the sphere, right? And using it to like remove some piece of the sphere. So what you end up with is like the stuff that's inside the sphere but below the cone. So like like the volume that I'm asking you to find is all of this junk, right? Is that making sense? Can everyone see it? It's just like you use the cone to pierce the sphere and like to just remove something from it. Is that making sense? Can everyone see the visuals of the picture? Now, okay, let's think about again like what the equations are. The equation of the sphere, right, is x squared plus y squared plus z squared equals 1. This is also something that you always need to do, right? You always need to rewrite the equations in like the corresponding coordinates. So this is in Cartesian, but we already talked about how to rewrite this in spherical. So how is this equation of the sphere in spherical? What does it become? Rho squared, yes. So it gives you rho squared equals 1 or rho equals 1. So that's the equation of the sphere, right? Now, the one that's a little bit more interesting is like the equation of the cone, because this is what you get. Now, what's the equation, like what was z in spherical coordinates? Go to the table that I wrote a bit earlier. What is z in spherical coordinates? It's rho cosine, right? Let me do it downstairs because I need more space. So we have what's the cone? It was z equals square root of x squared plus y squared. So this is rho cosine of phi. Okay. Now this is like a cool trick you can do in the middle. So what, instead of like switching this directly to spherical, what's x squared plus y squared? That's the r squared from polar, right? So this is also like the square. This is r, where r is the r from cylindrical or polar coordinates, right? Is that making sense? And what is R? This is something, sorry, that we can also go to the table. R is almost there. R is rho sine of phi, right? If you look at this. So you get this becomes rho cosine of phi equals rho sine of phi. So the rho's cancel, right? Because you can divide by both sides on rho. So you get 1 equals the tangent of phi. When is the tangent equal to 1? For what angle does that happen? Pi over 4, yes. So the cone just becomes pi over 4. It's the cone, because like if you think about it, this makes sense, because a cone, like this is saying the cone is just consists of all the points that are at an inclination of pi over 4 of the z-axis. Is that okay? Yeah, rotated 2 pi, correct, yes. And then, so what are the bounds for the integral? Again, like what you have to draw are like rays of light. So yes. So that's you see, like, so all these rays, where do they start? All the rays start at rho at the origin, right? Is that making sense? Like, let's just look at the picture for a second. They all start at the origin. So they start at rho equals 0, right? And where do they exit? They exit through the sphere still, right? So the bounds for rho are still rho equals 1. Yeah. Good. But now here is like the more interesting bounds for phi. What are the bounds for phi, right? Remember, phi is 0 at the z-axis. Phi is 0 at the z-axis. Yes, but the z-axis is no longer part of the region, right? Because we removed that with the cone. So really you start seeing the region until you get to pi over 4, right? So you start at pi over 4 and then you keep coming down, down, and down until you get to the south pole. So the bounds are from pi over 4 to pi. Is that okay with everyone? Is that making sense? And lastly, you still in theta is just like how much you're like moving, like how many quadrants or like this like region, like how many angle in theta occupies. It still goes from 0 to 2 pi, right? Because you still have to like do like a full revolution to get to all of the region. So the theta still goes from 0 to 2 pi. And ready for another one? This one is more tricky. Okay, let's try this one. This one is interesting. So now we're going to do the volume of the region outside the sphere. Let's do this. And inside the, inside the sphere, I meant. Inside the sphere. But outside the cylinder. Sorry. You mean in this problem that I'm writing? Like the picture will show you that there's like an obvious like in terms of bounds, you'll see that the picture like it's okay, like it will be fine in terms of the bounds. Yeah, let's draw the picture and you'll see like what I mean. So what's the first, like what's the equation of this sphere? What is that equation of the sphere? What radius does it have? And where is it centered? At 0, 0, 2, right? So here you go. Is that making sense? Well, it kind of looks like, I mean, you know what I'm trying to draw. It's just like a bit difficult. Oops. It is like, here's the center somewhere. The center is at 0, 0, 2. It's like radius 2. Okay, and then what's this cylinder? The cylinder, like what's this equation? This equation is really the equation of a circle, right? So you draw it here, but it's like the same thing that we have talked before, that strictly speaking, it's a circle that you get at each level, at each height. So that's how you end up with the cylinder. So it's like you insert a tube through a sphere, right? And the stuff in between is what I'm asking you to find the volume of. Is that making sense? Can everyone see the picture of what I'm trying to find? So far so good. Is like, and everyone visualizes. Is that okay? So yeah, it's in all directions. Let's go to our friend GeoGebra. That's the sphere, right? And then yeah, that x squared plus y squared equals 1. There's the cylinder. So you see, it's like right. It is like it's in like, you know, you're spinning something in 3D. So, but yeah, it's like in. It's just like imagine inserting a tube on a sphere and like just removing whatever. Like if it's an apple, you just drill a hole, right? Imagine making like a tunnel through the earth. So but there's like everything is connected. I think that's what you meant, maybe. Is that making sense? Is the picture now more clear? So here's a trick that you can do. Sometimes it's useful to write the equations first in cylindrical coordinates, even if you're using a spherical. So write the equations first. Before finding everything in spherical. So what happens if you follow this advice, right? This was like the equation of the sphere. What does this become in cylindrical coordinates? It becomes r squared plus z minus 2 squared equals 4, right? Is that making sense? And the other one was the cylinder was x squared plus y squared equals 1. And so this was like r equals 1. So why is this useful? Because if you go first through cylindrical, then you can draw this like cross section, or how, I don't know if that's the name that I gave them last time, on the RZ plane, right? So if you draw this here, this is what you get from these pictures. And maybe it's more obvious what we're looking at, because like the region of integration is just like this yellow cross section that you spin about the z-axis by 2 pi. Is that making sense? And now, like the idea is that these the rays that you need in spherical become on this plane. So here's the trick. So the part of the trick is that the continuation is that here the bounds for spherical can be found from the RZ plane by drawing radial arrows. Like just because remember, like the spherical arrows are like radial. So by that I just mean like you have to draw like arrows which start at the origin and are like this. They're like essentially similar to the arrows that you would draw for, you know, polar coordinates. They're not that different. So if you want to determine the bounds for rho, what you can do is do something like this. Okay. So where do the arrows, what do the arrows hit first? Yeah, they start at the cylinder, right? Yes, so they start at the cylinder, right? Excellent. The arrows hit the cylinder first, but what's the equation of the cylinder in spherical? Here you have to use in cylindrical, it would just be rho r equals 1. But what is r in terms of spherical? It was rho sine of phi, right? So what's the equation of the cylinder in spherical? Is cosecant. So that's the lower bound for rho. Is that making sense? Because the light rays will, like, which sort of makes sense. If you put like a light bulb at the origin, the light rays have to go first through the cylinder. Well, because this is a topic that's complicated. That's why there are so many tricks. But it's like, again, like you drill you stick a tube into a sphere, right? So if you place like a light bulb at the origin, right, like the light has to escape first through the walls of the tube. That's what this is saying. So that's okay. And then where do they exit? As someone said, they exit through the equation of the sphere, right? But again, the equation of the sphere in spherical coordinates. So this is like, we have the equation of the sphere in cylindrical. So we have to rewrite it to spherical. So this becomes like r squared plus z squared minus 4z plus 4 equals 4, right? I'm just expanding out the z minus 2 squared. So why do I do this? Because then the 4's cancel and you get r squared plus z squared equals 4z. But what is r squared plus z squared in spherical coordinates? I actually, someone had pointed this out on the chat before. Rho squared, good. And what is z? Is rho cosine of phi. And so you can cancel a rho on both sides.
What happened to the z squared?
Oh, this z squared here?
Yeah.
Is that it gets combined with r squared to become rho squared.
Oh, okay. I
Yeah.
remember.
Yeah. So the equation of the sphere is 4 cosine of phi. Is that okay? So far, so good? And then, yeah, let's see. Yeah, now do you see the angles? What are the angles? We need to find this angle, right? And we need to find this other angle. Those are like the places, those are the bounds for phi, right? Phi starts at this place and it ends at this place. Is that okay? So it's where the circle meets the lines, right? So the angles are found where the intersection occurs, right? So where is the intersection? The intersection is when both equations are the same. Both equations are like, we just found them, right? It's where 4 cosine of phi equals cosecant of phi. And you say, well, what is that, right? It's 4 cosine of phi equals 1 over sine of phi. This is 4 cosine of phi, sine of phi equals 1. I don't know if anyone remembers what is cosine times sine. Does anyone remember that this is sine of 2 phi? Oh, I just said it. So sine of 2 phi equals 1/2. And when is the sine of 2 phi equals 1/2? This is, I mean, it's like a special triangle, right? What is arc sine of 1/2? Better said. So 2 phi has to be pi over 6, right? And so phi has to be pi over 12. So that's one of the angles that you find, pi over 12. Okay. So here's pi over 12. And the other one is like, I mean, well, what is the other one? It's like pi over 2. I guess it should be, it's also like, it should all be kind of symmetric. Let's see. Well, because it could be sine, you know, or 2 phi equals like pi minus pi over 6, I think. So phi equals pi over 2 minus pi over 12. I mean, you know, like there are two options for the angle. So that gives you the other one. So I don't know how much that is, but I mean, this is phi equals like 5 pi over 12. So the bounds go from pi over 12 to 5 pi over 12. Good. And finally, what's the bounds for theta? It's just from 0 to 2 pi. So that was not too bad. No, actually, like if you're having trouble with these bounds, you'll have more trouble doing d phi d rho. We're never going to use d phi d rho. Like we're never going to switch the order for sphericals. It is a lot more complicated with d phi d rho. In fact, d phi d rho probably you need to use arc inverse functions like arc cosine, arc cosecant, a bunch of other things. It's like even worse. But we're never going to study it. Like all like for spherical coordinates, we're always going to write like d rho, d phi, d theta. Always. So it was a complicated problem. I don't disagree with that. Yeah, it's on the homeworks, but not on the exams. Like on the exams, like, you know, sometimes the homeworks have some other things for you to practice. But yeah, like, no, like it's the same with polar. In polar, we're only doing dr, d theta. I don't know if there's like a homework problem that uses d theta, dr, But yeah, like in spherical and polar, like somehow like the right order is d rho, d theta, and then dr d theta. Yeah. Is that okay? Yeah, so like it just takes some time to digest this example, but it is there. Like you're right, besides the MyLab problems, like if you look at the old exams, there are 7 practice exams. So there should be at least 3 or 4 which are in spherical coordinates. So also take a look at those. And I'll send you an email in a second just suggesting some more problems on spherical. Okay, but this is more or less the last topic for the exam. So on Thursday, we do have to start a new topic because we're running behind, a little bit behind, not too much, but we do. It's related to double integrals, so we're still going to be doing double integrals. That's a good thing. Okay, but yeah, I'll see you on Thursday. The exam is next month. Yes. See you. You too.